Hello again. This is Ishai from Origin GPS, and this is our second tutorial about how to operate and develop with OriginIoT. This second tutorial will be focusing on the OriginSmart API specification, the basic protocol messagings, and I will show how to implement this using our development environment. So let's start from the top. I will just run through this document and explain how to read it. So this is the high-level description of the system. Basically, you have the Cortex M4 and its peripheral interfaces, internal interfaces to cellular module and the GNSS module by Origin GPS. And the idea of the system is that you don't want to, and you don't need to upload any new firmware to the ARM Cortex MCU. You can control all the peripherals from the cloud, and also some functions allow you to determine the behavior of the machine itself. But main idea is to operate almost any type of sensor or a device that can work with these interfaces from the cloud without any need to install new drivers or to make any changes in the firmware. So this is the goal of this document, to educate and teach and train how to use this system method. The first thing you want to know that we defined, we defined the interfaces and the interface IDs. Each interface has an interface ID that you need to know in order to write or read from it. So, for example, the MCU is interface 00. The end application in the cloud is interface 80. And for example, let's look at the external ones. You have the I2C, which is important because you can connect over 100 devices to it. So this is interface 05, and you got some GPIOs and it interfaces 0A to 0D, and the wake up pins and the SPI and analog to digital. It's all in this table. So about the connection to the cellular network, this is something that you will want to understand if you want to design your own server. This is the connection sequence. You should go over it if you want to know which types of messages to send to the device from your server and what to look for. So this is it. If you're using our device, our server, you don't need to implement this. This is already implemented. Okay, let's go on to the basic message format. This is a very simple header and raw data type messaging format. All messages start with 2 bytes of message length, termed count. This is 2 bytes. The source interface is where you are sending the message from. For example, if you are sending a set message from the cloud, this will be a 08. If you are sending, if you are getting message back from the device, this will be the interface that issued the message. If it's from GPS, it will be 03. If it's from any I2C device, it will be from 05, for example. The destination interface is where you are writing to. For example, you want to write to your accelerometer on the I2C, you should put 05 here. Now the next byte is the type of message. The message type could be get or set. Get is getting device from a remote interface, and set is writing to a device. Response is what you get in return, if from a get message or or from set message. ACK is acknowledgement. Notify is a notification issued by the device. And multi-get and multi-response are just messages that repeat the get and response with your predetermined rate and a sample rate and times. We will go over it in a different tutorial session. The expected acknowledgement could be turned on and off, meaning just if you are expecting the device to send an ACK message or not. Expected response, it's for a set message. It's just determining if you are looking for a response from the device or not. And expected number of bytes is only for get messages. As it says, it's the number of bytes you expect in your next response. And this table just clarifies what we just went over. So this is the header values, and the device header and device raw data are dependent on the type of interface you are writing or reading from. So let's start with the UART. The UART based interface has two types. It could be used to interface with a peripheral device, and in this case you are only sending data. For example, the GPS is connected to a UART interface, so if you want to send data and to operate the GNSS module, you will just have to use the NMEA protocol, which will be specified later. But the UART based message definition are also used to communicate with the MCU, setting the MCU configuration and behavior. For example, this is a back from reset notification. This will be the two next bytes after the header, and it is used, for example, for parameter configuration for your interfaces. This is how your interfaces work. So it's different from type to type. This is for GPIO. This is for a UART interface. As you can see, it kind of determines how you configure your interface, the baud rate, RTS or CTS, are they disabled or enabled, stop bits, parity, and everything you know from a normal UART interface. Same idea for I2C, SPI, and this is the response you will receive from the MCU if you send the correct message. This is module registration. This is what your server should look for when he's putting up the list of connected devices. Module app keep alive notification. The module is sending these once every 30 minutes. It's issuing a keep alive notify just to keep the line open. And the loopback test is something that the server can issue to check periodically if the device is still on and online. As we'll see, we're adding a device header type. So if you want to send a get message, you should specify the device address and where do you start reading from. I will show an example. And if you're sending a set message, you need to send the device address on the I2C bus, the reg start, the number of bytes that you are writing, and the data itself. Um, the response is very similar to the get message, and the multi get and multi response will be addressed in further sessions. GPIO is very simple. You send the data, you get the data, set it. Really straightforward. Okay, so you can go over the default configurations just to be acquainted with it, and we will have a session separately on the GNSS functionalities. There are some sample messages that you can use, test your development kit. That's it. Let's go to the development environment. To reach our development environment, operate your browser and go to OriginIoT.com. Here, click on Origin IoT Labs, and you will be redirected to our development environment. Alternatively, you can click this address on the address line of the browser and reach the same place. Make sure you have your credentials to log into our server beforehand. You can get them from your Origin GPS representative. After you type in your credentials, your username and password, click on the click signal and you will be logged into your list of modules. The list of modules are modules that are registered under your account, and they are identified by the IMEI, International Module Equipment Identifier. And this model ending up in 554 is already logged in. You can see it by the status. To learn how to connect a module to a cloud, go to tutorial number 1. When I click on this, I reach my module manager page. These devices are pre-configured to, while they're connected, to send GNSS message once every 5 seconds with location. This is the RMC message. You can change it by sending an NMR message via interface 03, the interface of the GNSS, to stop this or to change the rate. We will go over it in a different tutorial. But what's interesting about the GNSS message that we can learn a lot about the messaging protocol from it. This is a notify message because it's issued by the device. It's just a notification and not a response on other set command. And we can see the protocol here. It starts with 002F. This is the length of the message. 2 bytes are for it. This 03 is the interface ID, the UART that is connected to the GNSS module. 80 is the end application. So we're sending from the UART of the GNSS to our end application in the cloud. 01 is the type of message, notify. 20 is the acknowledgement flag, which is turned off, as we don't need the server to send acknowledgement for the module for each of these commands. And from here on, it's the hex representation of the NMR string that is sent from the command. For example, 24 is a $sign and 47 is G, etc., etc. We currently don't get valid location because we're inside a building and GNSS does not work well inside of buildings. If we go outside, this will change to A and you will see all the location information. I want to show an example of how to use simple set and get message to operate ADXL345, the accelerometer that is connected to the I2C bus. First, I will add a new message by clicking this green plus sign. And let's say, for example, that I want to write into a certain register in the accelerometer DSP, the register that sets the data format. So what I need to do is to type in some name that will help me in the future to remember what I did. The count byte updates automatically in this development environment, so you don't have to worry about it. This is a set command because we are writing to a register. The source is 08 because we're writing from the end application. Expected acknowledgement I'm turning off. The destination is 05, the I2C interface ID. Expected response, I do expect a response, so I'm setting it to 1. Now let's see what do I need to write in the device header. I will go to the API spec and open it on the I2C page. And for a set message, my next byte is device address. Device address can be configured by looking into the datasheet of the accelerometer. It is also mentioned in the user guide, but I want to show you a cool way to do it using the debug console. You can type in I2C 0 Pro and enter. This will count the number of devices on the bus and show you their addresses. A6 is the address of the accelerometer. This is a very useful function. If we go back to our development environment, you can already type this. Now, what is the next byte? The next byte is the reg start, to which register I want to read. For this, I will need to open the datasheet of the accelerometer. These are usually very easy to find online. And let's look for the register map. Almost any I2C module has them in the datasheet. Data format. Now I can look for the data format byte, and its register address. This is 31. So I can say that I want to write to register 31. Now the next byte is the number of bytes I'm writing, 01. This is a 1 byte register. And the data. So now I need to go and look what do I want to send here. Let's look for it. This is the data format register definition. Self-test bit, I want to set it to 0, SPI bit 0, int invert. I don't want to use interrupt right now. Full resolution bit will be also set to 0. The justify bit will be set to 0. And the range, let's set it to plus minus 4G, 0, 1. So the data that I will send, that I will write to this register, will be 0, 1. All I need to do is save, and this message is ready. If I operate it, you can see that the string is sent to the module. In the debug console, it will look like this: a set message and a response message issued. this is how we write to a register. If we want to get data from the accelerometer, we need to set a get command. The source is again 080, because this is the end application issuing this message. We don't need acknowledgement. Destination is 05, and the expected number of bytes are 6, 2 bytes for each axis. We are looking for the axis, and let's go back to the register map to look at. We know that the device header, the address of the accelerometer is A6, and we just need to find the register from which to start reading. Register map, and let's look for the data to read from. Okay, we have 6 bytes starting at 32x. So this is the message that we need. I added the previously message to wake up the device from sleep mode. This is it. This is the result of the gate data. We see the header message. And right after the header, let's just filter these GNSS messages so they don't interrupt analyzing the data. So after the header and the device header, we see the raw data. We see 2 bytes for the X acceleration, 2 bytes for the Y acceleration, and 2 bytes for the Z acceleration. A 0,1 is a very small acceleration, probably some noise. F5, because it comes into complements, this is a minus, very small number. In 78, this is a slightly larger number, meaning that the sensor senses acceleration in the z-axis. This is the gravity, and this makes sense. Just to make sure that it's working, I will put the device on another position orientation, and we'll see that we get different message here. Now we have a larger number on the x-axis and very small values on y and z. So this was a simple demonstration on how to operate simple set and get messages. Then our next tutorial will be more advanced, showing multi-get and multi-response messages and widget configuration. I hope this helps, and see you soon.